Welcome to lecture number 11. We're going to continue our discussion on hydrocarbons today. So we talked a little bit about hydrocarbons as well as nomenclature in the last lecture. So we left off last time with a few terms that I've written here, staggered and eclipsed we saw. And now we're looking at conformations here of butane, 4-carbon chain, butane. Now, remember for these Newman projections, we are looking down this CC bond where here's our perspective and we're looking down this central CC bond. So if we look, well, I'll actually draw the eyeball from the other side here so that this first structure makes more sense since I drew it from this perspective. Either way, we're looking down a CC bond. So if we're looking down this CC bond, we see a methyl group up above us, and in the back it's coming out on the bottom side. Okay, so that would be this first conformation, this staggered conformation here. Remember, staggered is the best. Okay, we want everything to be spread out as much as possible, just like Vesper theory. The atoms, the substituents, want their space as much as possible. So the staggered conformation is the best, where everything is about 60 degrees apart. Eclipsed is when we have things bumping into each other. And the way that we can go from staggered to eclipsed, remember, is by rotation of this CC bond. Okay? If you're not comfortable understanding how bonds can rotate, or if you're having trouble visualizing these, then I highly recommend building a model using a molecular model kit. And you can hold these molecules in the palm of your hand and look at them from every angle, perspective. You can look down the CC bond and look at the Newman projection. It's really, really helpful for understanding how molecules exist three-dimensionally. The molecular model kits are built in such a way that when you construct molecules, they look very similar to how they would exist in real life, with bond angles, torsional strain, etc. Okay, so looking back here, we have butane, staggered conformation and eclipsed conformation. Again, rotation of the single bonds is how we can go from staggered to eclipsed. Both of these carbons that I highlight in red, if you build a molecular model, you can sort of grab these carbons and twist them back and forth. Every single carbon can be twisted in this way, but when we're considering these Newman projections, we're really considering the rotation of this single bond between these two red carbons, considering the rotation of that single bond that we're looking down. Okay, so hopefully you can see how we can get between different conformations by analyzing the rotation of that bond. Now for butane in particular, we have to be cognizant of the fact that we have this large methyl group as a substituent. Methyl is much larger than these little hydrogens I'll circle in blue. Okay, the methyl group is much larger and takes up much more space, so therefore it's going to want to be staggered even more. And ideally, these methyl groups want to be staggered 180 degrees apart from each other. Okay, this is what we would call the anti-conformation. Anti, meaning that they are on opposite sides of each other. Okay, these two large methyl groups are on opposite sides of each other. Now we also have gauche as a staggered conformation. So gauche is a type of staggered conformation I drew over here on the right. And this is when these two large groups are not on opposite sides, but they're 60 degrees apart. They're right next to each other. So gauche is reasonably stable. It's sort of in the middle because it's staggered, which is good. But the largest groups, in this case the methyl groups, aren't on opposite sides, but adjacent to each other. So gauche is sort of in the middle in terms of stability. Again, staggered with an anti-conformation is the best because these two large groups are as far away as possible. We can also sort of look at eclipsed in the same light. So eclipsed, we could have like this as I drew, But we could also have an eclipse conformation where the two methyl groups are eclipsing. And this would obviously be even worse. If I drew an eclipsed conformation here where we have a methyl group eclipsing with a methyl group, that would be the worst possible conformation because our two large groups, methyl groups, are literally right on top of each other. Okay, so this would be the absolute lowest and highest in energy, lowest stability. This would be the worst conformation possible. Okay, again, both of these are staggered. I'm sorry, both of these are eclipsed. Whoops. Both of these are eclipsed. Okay, both are eclipsed. But this one on the left is a little bit worse, a little bit higher in energy, a little bit less stable. There's a lot of different ways to say it. I'm just going to say that this one in the box here is a little bit worse because the two largest substituents, the methyl groups, are eclipsing each other. It's not as bad on the right because the methyl groups are only eclipsing a small hydrogen, and that's okay. Okay, I mean, it's not ideal, but it's much better than the two methyl groups eclipsing each other. Okay, so now I'm going to draw or consider a cycloalkane. Okay, we've talked a little bit about butane and straight chain carbons. Let's continue our discussion now considering ring systems. So I'm going to look down this CC bond in cyclopropane and draw a Newman projection. Now the ring system is going to come out over here and come back. Okay, we're looking down that CC bond. And again, this circle I'm drawing here is just a placeholder for three-dimensionality, giving us some three-dimensionality where we can now see we have this front carbon, which is in front of the circle, and then we have a carbon in the back, which is hidden by the circle. The circle doesn't represent an atom or anything chemically. Okay, the circle is just there for three-dimensionality. Now on the front carbon, we have an H and an H. And on the back carbon, we have an H and an H. Now you'll notice on this structure, when I drew it, this does not look very staggered. Our groups are quite eclipsing, right? Our groups are very close to each other. Why are they close to each other? Well, because they're sort of tied together by this ring system, right? This three-membered ring. We can't break that ring system. So this ring system is sort of holding these two carbons in a semi-eclipsed conformation, which is actually it's making the molecule less stable, okay? This is one reason why three-membered rings are not very stable. There's two considerations we have to consider. One is the angle strain. That's the ring angles. And the other is the torsional strain. That's the eclipsing groups, okay? So these are two very important concepts when it comes to ring systems or cycloalkanes. Looking back at this Newman projection I drew, in a three-membered ring, there's a lot of torsional strain because we have these eclipsing groups, right? These carbons are sort of locked into this conformation, and we have these eclipsing hydrogens, which introduces a lot of torsional strain. There's also a lot of angle strain in a three-membered ring because this angle here, every single angle in this three-membered ring is less than the natural angle of a tetrahedron, okay? These angles are about 60 degrees, right? About 60 degrees. We know that the angles of a triangle add up to 180 degrees. So each of these angles is about 60 degrees in cyclopropane. But remember, in a natural tetrahedron, every angle between two groups is 109.5. Okay, about 109.5. So this angle is much tighter, and it's bringing these two groups much closer together than they want to be. So cyclopropane, the smallest possible ring that we can have, is quite unstable. Why? Because there's a lot of angle strain. The angles are very small and very tight. There's also a lot of torsional strain because we have these eclipsing groups. Okay? So this is a very unstable ring system. 3-membered rings are quite unstable. 4-membered rings, again, quite unstable, although not as unstable. 5-membered rings are a little bit better. And the 6-membered ring is the sweet spot. Okay? The 6-membered ring is the sweet spot. 6-membered ring, there's very little angle strain and there's very little torsional strain. So the 6-membered ring is actually the most common ring system in nature, the most common ring system in organic chemistry, and that's a testament to the fact that it's so stable. Okay, why is it so stable compared to the other ring systems? Because it has very little torsional strain and it has very little angle strain. The angles in these bonds are very close to 109.5, which is the natural desired angle for a tetrahedron. So these are the two considerations right here that we are going to keep in mind as we look at this 6-membered ring system. Okay, keep these two things in mind: angle strain and torsional strain. So I'm going to draw this 6-membered ring here. This is going to be something that we will see very frequently, very often, because 6-membered rings are so common. We will also see some 5-membered rings, some 7-membered rings, some 8-membered rings, but 6 is by far the most common. Okay, so you'll definitely get used to drawing 6-membered rings. Now, let's take a look at this ring system 3-dimensionally. Okay, so I'm going to draw something here, and we will get a lot of practice drawing this. To draw a 6-membered ring 3-dimensionally, first draw these two parallel lines where they're just offset a little bit, and then make a little tooth shape down here, connect those with a triangle pointing down, and connect these two with a triangle pointed up. Okay, now once you're all said and done, you should have a bunch of parallel lines. See all the different parallel lines here. We have this line here is parallel with that one. This line is parallel with that one. This line is parallel with that one. Okay, so there's lots of different ways you can draw this shape here, but that's how I like to do it. Just draw two parallel lines and then connect them with triangles. Either way, what we're looking at here is called a chair conformation. And this is the conformation or the shape that a 6-membered ring takes. And this is why the 6-membered ring is so stable. Okay, so here's the 6-membered ring drawn as a chair. I'm going to add in the hydrogens. Now keep in mind the two things I mentioned before. I'll type them up here: angle strain and torsional strain. Okay, keep those two things in mind. Now, I'm actually going to draw this a little bigger since this will be important. Let's draw it right here. Okay, so here's our chair. I'm going to draw all the hydrogens in. Now to do this, what you do is you draw straight up and down lines. Wherever you have an uptick, you draw a straight up line. Wherever you have a down tick or a downward facing vertex, you draw a downward line. Straight up, straight down. So you end up with 3 lines that are straight up and 3 lines that are straight down. Okay. Now, these are called the axial positions. Axial. Maybe I will highlight them in red. Okay, let's do a red for all the axial positions. And then maybe we will do a blue for the equatorial positions. Equatorial. Let me get my blue. Now for the equatorial positions, doesn't matter really how you draw them. Typically, I will draw them about parallel with the next line over. So this blue line, I'll draw parallel with this bond in the ring over here. Okay. This one, I'll draw parallel with this line over here. So you skip a bond and draw a parallel line. Although it doesn't really matter how you draw it. Really, what you want to do is just draw it away from the ring system, kind of like this, just sort of pointing out into free space. Okay. So these are the equatorial positions. Now keep in mind, everywhere that we have a carbon, I'm going to draw a green dot wherever there's a carbon at each vertice. Each of these green dots is one of these 6 carbons on the ring, and they are all in the shape of a tetrahedron. Remember that. They're all in the shape of a tetrahedron. Now, looking at this chair, looking at this ring system, all of these angles are very close to the true shape of a tetrahedron. They're all almost 109.5, which is what we want when we consider angle strain, right? That's what we want when we consider the angle strain. All of these angles in the ring system are very close to 109.5, okay? And that's good because that's how much we want all of these substituents to be spread out around each of these green carbons, okay? Now considering torsional strain, there's very little torsional strain in a 6-membered ring system, okay? And we will draw some Newman projections where we can see how we can get staggered conformation around each CC bond. But the one consideration that we do have to have when we consider ring systems like this is that there's something called 1,3 diaxial interactions. First, let me draw all the hydrogens in. Okay, and then we'll talk about 1,3 diaxial interactions. Let me draw it here. Okay, 1,3 diaxial interactions. So this is the major consideration that we have to take when we consider torsional strain on a 6-membered ring. All this means is that the axial positions are worse for larger groups. Axial positions, shown in red here, are worse for larger groups. Okay, why is that? Well, if we imagine, say we have a CH3 here, and say we have a CH3 up here, say we have some large groups in these 2 axial positions here. These 2 large groups are going to be bumping into each other here if they're at the axial position, because the axial positions are going straight up and straight down relative to the ring system. So if you have 2 atoms, 2 substituents that are large in the axial positions, then they're bumping into each other, okay? Or they're bumping into the hydrogen right here. Either way, they're bumping into whatever's on top or whatever's below the ring system. The equatorial positions are a little better because if we have a large CH3 out here in the equatorial position, sticking out into free space, there's much more space for it to exist, and it's not bumping into anything as much as it would if it were in the axial position. Okay? So that's the big consideration for ring systems, 1,3 diaxial interactions, which simply means that large functional groups methyl groups, anything bigger than a hydrogen does not want to be axial. And generally speaking, the larger the group, the less it wants to be axial, okay? So keep that in mind as we move forward. Now, ring systems, like this chair system, can flip. Okay, this ring system can flip. What do I mean by that? If you build a model, you can actually see exactly what I mean. Let's number these. Let's go 1, 2, 3, 4, 5, and 6. Okay. Now this 6-membered ring, see how this carbon numbered 1 is pointing upwards? This carbon numbered 1 could point downwards instead, and this ring could invert itself and flip the other direction simply by pulling. If you have a molecular model kit, you simply bend number 1 here. If it's in your left hand, you would bend it down and you would pull 4 upward. And you'll see that this ring can flip or invert. And this ring can then become like this: 1, 2, 3, 4, 5, and 6. Now I'll color code with the exact same colors. Now on carbon number 1, this red hydrogen was pointing upward, and it's still going to point upward, but now it's in an equatorial position. And the blue hydrogen, this blue bond here, is pointing downward. Now it's an axial hydrogen. See how it flipped? So this red hydrogen used to be axial, but if you do a ring inversion or a ring flip, that red hydrogen now becomes equatorial. It's still upward. It's still the hydrogen in the same position. All we're doing is bending the ring so that we make a different chair conformation, okay? So this sort of looks like, one thing that people say, it looks sort of like a beach chair or a lounging chair where you can lay with your head up here and then your body down here. There's your legs, okay? So it looks like a chair because it kind of resembles a beach chair, okay? All we're doing is we're sort of flipping the chair, bending it around so that now you're facing the other direction, okay? Then your head goes up towards carbon 4 like that. That's one way you can think about it if you're confused about the chair inversion here. At the end of the day, carbon number 1 is still carbon number 1. It still has the 2 groups attached to it, still has these 2 hydrogens. We're just tipping it so that it's facing downward instead of upward, okay? So every time you have a cyclohexane, it can exist in one of 2 chair conformations, okay? Depending on which end of the 6-membered ring is facing up and which end is facing down. So let's go through here and we'll draw all of our red hydrogens. Red is down, then we have red is up on 3. So red is up on 3. And on carbon 4, red is down. On carbon 5, red is up. And on carbon 6, red is down. Okay. Then we can fill in with blue. Blue is axial, 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 axial. Okay, so during a ring flip, all of the axial positions become equatorial, and all of the equatorial positions become axial. Now their relative position doesn't change, okay? If you consider these 2 structures, these 2 ring inversions, we'll call this 1 and 2. In structure 1 on the left, all of the red hydrogens that I drew are all axial. 3 of them are facing up, 3 of them are facing down. okay? And if you look at that structure on the right, all of those red hydrogens are now equatorial. So all the equatorial positions became axial and vice versa. Now the relative positions never change. Let's just take hydrogen, let's take carbon 5, for example, looking at carbon number 5. The red hydrogen is still facing up. The blue hydrogen is facing down. Let's look at 5 on structure 2. The red hydrogen is still facing up and the blue hydrogen is still facing down. We're never breaking any bonds, right? We're not making any bonds or breaking any bonds. We're simply changing the conformation or the shape of the molecule. And the molecule will do this spontaneously. It will flip back and forth between these two chairs, depending on which one is more stable for it. So if we have a 6-membered ring, it could exist in this chair over here, number 1, could exist in chair number 2, or it could exist anywhere in between, okay? These are just the most stable conformations or shapes that these 6-membered rings can take shape, okay? 6-membered rings, there's a lot to learn for 6-membered rings, a lot to think about, but at the end of the day, just practice drawing these 6-membered rings, practice drawing the equatorial positions, practice the axial positions, and then practice this ring flip, where you flip the ring and you draw the chair in the opposite way, and then you flip all the axial positions become equatorial and vice versa. And remember, when you do that, you're never breaking or making any new bonds. Whatever was facing up is still facing up, okay? It just goes from being axial to being equatorial, okay? We're going to get a lot of practice on this in the workshop, which will be the next video. But let's just look at an example. Let me actually clear this out. And let's look at a molecule here. Let's draw okay, so we will talk much more about stereochemistry, wedges and hashes in a future chapter. But for now, just for simplicity, let's take this molecule and let's draw it in 2 different chair conformations and determine which one is more stable. So let's draw both chairs. And determine which one is more stable. Okay, so the first thing you do is you simply draw a chair. It doesn't matter which one. I'm just going to draw it like this first. Okay, there's our first chair. And let's go ahead and draw this. So we have a methyl group here. Okay, we have a methyl group. Let's number these carbons. 1, 2, 3, 4, 5, and 6. I'm just going to call this one over here on the tip generically 1. Okay, let's call this carbon 1. Now we have a methyl group in the up position, and we have a hydrogen in the down position. Remember, anywhere you have a down vertice, you have a down axial. And anywhere you have an up vertice, then you have a vertical upward axial. So I think it's always easiest to draw your 6 axial positions in. 1, 2, 3, 4, 5, 6. We have 3 ups, 3 downs, and they're alternating. And then you can fill in with your equatorial positions. Okay. The equatorial positions just all point away from the ring system. So on carbon number 1, we have a methyl group in the up position. So I think it's always easiest to draw your skeleton here of the ring system of the chair. And then once you have your skeleton drawn out, then you can fill it in. So this right here in this box, get very comfortable drawing that conformation, drawing this, and then also the inverse of it for the other chair. Okay, start with this. So we start here. Now on carbon number 1, I'm just going to call it this carbon on the tip. It could be any carbon. You could call this one over here carbon 1 or this one. It doesn't matter. Okay, it's all relative. So this is carbon number 1 over here. A methyl group is in the upward position. Remember, a wedge is facing upward. Now you could also flip this molecule upside down and it would be in the downward position. We'll talk more about that in the stereochemistry unit. But for now, in terms of simplicity, let's simply draw this out. Hydrogen in the down position, and we have a methyl in the up position. Okay. Now everything else is a hydrogen. And we've drawn our first chair system. Okay, there it is. Now let's draw the ring inversion, the ring flip. And to do this, we draw parallel lines in the opposite direction. And then our leftward tip is down and our rightward tip is up. I'm actually going to draw that whole thing a little bigger because we have the space here. Leftward tip is down, rightward tip is up. So we've inverted the chair. Let's draw in all the axial positions. 1, 2, 3 up, 1, 2, 3 down, and then the equatorial positions facing away from the ring system. Okay, so we've drawn our skeleton. If this is carbon 1 over here, now it's important that we make carbon 1 this carbon over here, or any upward facing axial position. Because this methyl group, if we consider carbon 1 over here and carbon 1 on the right, this methyl group is in the upward position. It's going to stay in the upward position, but during the ring flip, it will become axial, because on the left, it's equatorial. So if we did a ring flip, a ring inversion, this methyl group is now axial. Keep in mind that methyl group still needs to be in the upward position, so it could be on any of these 3 upward axial positions. Okay. That hydrogen is still there in the down position. Now it's in the equatorial position. And all the other atoms are hydrogens. So there we have our 2 rings. Okay. Now, which ring is more stable? We have 1 and we have 2. Which one is more stable? Well, remember, large groups want to be in the equatorial position. So with that in mind, this methyl group is going to prefer in the equatorial position. So it's going to be more stable here in number 1 on the left. That methyl group wants to be equatorial. Why does it want to be equatorial? Because larger groups do not like being in the axial position due to the 1,3 diaxial strain with these other axial positions. Now it's called 1,3 diaxial because if we continue numbering 1, 2, 3, every other carbon is axial, so we call it 1,3. The first carbon, the third carbon, and the 5th carbon are all have 1,3 diaxial interactions. Okay. And again, those larger groups want to avoid that 1,3 diaxial interaction, so they would prefer to be equatorial. Now here's a chart that I'm showing, which shows the relative 1,3 diaxial strain based on the functional group, and you'll notice the general trend that as you increase the size of the group, you increase the 1,3-diaxial strain. Okay, so what this means is that the larger the group you have, the more it wants to be equatorial. Okay, there's more strain associated with a larger group being in the axial position. So with that in mind, let's look at one final example. Where we have a couple different groups on it. So let's do the same thing. Let's draw both chairs and determine which one is more stable. Okay, here we have an ethyl group, ET, ethyl, so that means 2 carbons. And we have a chlorine, Cl. Okay. Let's draw our 2 chairs. Let's start off with one here like this. Okay, let's fill in our axial and equatorial positions. I like to do all the axial positions first. And then fill in with the equatorial. Okay. Now let's write this out. We have an ethyl in the up position. Now for the beginning, it doesn't matter what you choose, right? We could pick any carbon here. We're gonna just have to make sure that the rest of our work is relative to what we start with. So I'm gonna draw ethyl on this carbon over here in the upward position, right? The upward position because it's a wedge. So that means there's a hash with a hydrogen back here. And that means on this carbon, there's a wedge with a hydrogen, right? These are implicit hydrogens. Okay. So on this carbon with the ethyl group, right? This ethyl group is coming upward and the hydrogen is in the back. The hydrogen is downward. Okay. Now going clockwise around this ring, that means we have a CH2 on the next one. And then the carbon after that, there's a chlorine in the down position and a hydrogen in the up position. Okay. This chlorine on the third carbon is down, the hydrogen is up. Make sure you have those relative positions in mind. The rest are hydrogens. Typically, you don't have to draw those in, but I'm just including them for clarity. Okay, so ultimately we have an ethyl group in the up position. 2 carbons away, we have a chlorine in the down position. We can number them 1, 2, 3, right? 1, 2, 3, where that third carbon has a chlorine in the down position. Okay, so there's the first chair. Now to get the other chair, we draw the parallel lines in the other direction. Draw a downward tip and then an upward tip. Fill in our axial positions. Fill in the equatorial positions. Now we can't just pick anywhere for the ethyl group to be. We have to think about what's going to happen here. We have to pick a specific carbon for it to exist on. Now our ethyl group in the first structure here, our ethyl group is upward and it's axial. It's going to stay upward but become equatorial, right? So what would be a good carbon to draw this on? This one would be good right over here, ethyl, because it's upward and equatorial. You could also draw the ethyl group here, right? That'd be another good position for it, or you could draw it here, okay? I drew it in the first spot because it's very similar to the spot where I drew it on the left there, so we can visualize that ring flip, okay? Either way, when you draw your ring flip, make sure that your functional groups stay in the same spot and then simply become axial to equatorial or vice versa. Okay, so carbon number 1 here, ethyl group is up. It used to be axial, now it's equatorial. Let's go carbon number 2, and then carbon number 3. Our chlorine is down, and it should now be axial, which it is. And then we have a hydrogen. Okay, so there's the ring flipped product. Again, notice how the chlorine and the ethyl are changing from axial to equatorial and vice versa. They're never changing relative position. The chlorine is always down and the ethyl is always up, but they are simply changing axial versus equatorial. Now, which ring system is more stable? Well, on the left here, on structure number 1, we have an axial ethyl, and we have an equatorial chlorine. And on the right, we have an equatorial ethyl and an axial chlorine. So what we have to do for a question like this is consider which of these is larger. We have an axial ethyl here, and we have an axial chlorine here. We can almost consider there to be no negative interactions for equatorial groups. So this ethyl being equatorial on structure number 2, or this chlorine being equatorial on structure number 1, we can almost not consider them because there's very little negative interaction with equatorial groups on these ring systems. It's all about the axial position. So comparing the two axial positions, ethyl or chlorine, which one is less stable? Well, you can refer to the chart, or you can simply consider which one is larger, an ethyl group or a chlorine. An ethyl group is larger, right? Because it's 2 carbons connected to each other, and then each of those carbons, you have 5 hydrogens around. So it's a much larger group. So that ethyl group would much prefer to be in the equatorial position, which would be structure number 2. More stable. Again, because the ethyl group, the larger group, is in the equatorial position as opposed to the axial position. Okay. Now you could refer to the chart. An ethyl group in the axial position is about 8 kilojoules per mole in energy, and an axial chlorine is about 2 kilojoules per mole. I'll write that here. An axial ethyl is about 8 kilojoules per mole, and an axial chlorine is about 2 kilojoules per mole. Okay, so we can see that the axial ethyl is much higher in energy, much less stable. So therefore, structure number 2 is more stable because that ethyl group is in the more stable equatorial position. Okay. So again, with these ring systems, keep in mind that this ring over here on the left, this 6-membered ring, and any 6-membered ring can exist in one of 2 chair conformations. Okay, one of 2 chair conformations, either the one on the left or the one on the right. Okay, structure 1 or structure 2. Now, these 2 chairs are going to be different in energy based on what groups are in the axial positions. Okay, and again, that's because of those 1,3 diaxial interactions, which causes the axial position to be much less stable for those larger groups. Okay. So the final thing I want to touch on is the idea of fused rings. Fused ring systems. Now, this is something that you may see, you may not see, but I'll just mention it. Now you could have a 6-membered ring like this fused to another 6-membered ring that looks like that. Okay, now these two rings are fused together, and you could have a hydrogen here and a hydrogen here. And if these two ring systems are fused together in a way such as this, you would call this a cis-Decalin system. Cis-Decalin system. Okay, Decalin because there's 10 carbons altogether, and cis because these two hydrogens are both facing upward. So that's how you draw the chair systems for a fused ring system like that. You could also see the trans-Decalin ring system, which would simply be like this. And in this case, you have a hydrogen pointing down and a hydrogen pointing up. Again, this would be called the trans-Decalin ring system. So you could have fused ring systems like this. If you go into more advanced organic chemistry, you'll see systems like this more commonly. But it's just an idea to be aware of. Okay. So overall, there's quite a bit of new material in these lectures. If you didn't get it the first time, watch it through one more time, and we'll get a lot of practice on these in the next workshop. Drawing ring systems, drawing Newman projections, and understanding what makes a stable conformation and what makes an unstable conformation. Okay. Okay, that's everything for this lecture. I'll see you in the workshop.